And the craziest part is, even with all that redundancy, a single poorly chosen data structure in one critical path nearly brought down their entire recommendations engine.
Wait, are you talking about that Netflix outage last year? The one where everyone thought it was a DDoS attack?
The very same. Turns out it wasn't some sophisticated hack. It was a good old-fashioned algorithmic complexity bomb, ticking away in plain sight. Everyone was so focused on distributed systems and microservices, they forgot the fundamentals.
So, beyond the headlines, it boils down to picking the right tool for the job, right? We're not just talking about academic exercises here, we're talking about real-world impact.
Exactly. How many times have we seen perfectly good code choke under load because someone defaulted to an array or a hash map when something more specialized was needed? It's like using a hammer to screw in a light bulb. It might work, but it's going to be messy, inefficient, and potentially disastrous.
Okay, so let's get specific. We all learn about trees, graphs, heaps, and tries in school, but when do they actually come up in real-world scenarios? What are the hidden gotchas that textbooks don't tell you?
Let's start with trees, shall we? Specifically balanced trees. Think about how Uber's dispatch system works. They need to efficiently find the nearest available driver to a rider in real time.
Right, a spatial query. Naively, you could iterate through every driver and calculate the distance, but that's an O of N operation, and with millions of drivers, that's a non-starter.
Exactly. That's where spatial indexing comes in, often implemented using a variant of a balanced tree like a KD tree or a quad tree. These structures allow Uber to quickly narrow down the search space, finding the closest driver in logarithmic time. The crazy part? These trees aren't static. They're constantly being updated as drivers move around the city.
But wait, doesn't that constant updating introduce its own performance bottlenecks? Rebalancing a tree after every single driver movement seems expensive.
It can be. That's where the self-balancing part comes in. Algorithms like AVL trees or red-black trees are designed to minimize the cost of rebalancing, ensuring that the tree remains relatively balanced even with frequent insertions and deletions. They do introduce some overhead, but it's a worthwhile trade-off compared to the alternative of scanning the entire dataset. Also, Uber likely uses some clever caching and batching strategies to further optimize these updates.
Okay, that makes sense. So balanced trees for spatial indexing in Uber. What's another example where trees shine?
Think about compilers. Every time you write code, the compiler needs to parse it and build an abstract syntax tree, or AST. The AST represents the structure of your code, allowing the compiler to perform semantic analysis, optimization, and code generation.
So the tree structure reflects the hierarchical nature of the programming language itself.
Precisely, and the efficiency of the compiler heavily depends on how efficiently it can traverse and manipulate this tree. A poorly designed AST can lead to slow compilation times and even introduce bugs. It's a classic case of data structure choice impacting the entire user experience, even though the user never directly interacts with the data structure.
Interesting. So Uber for spatial search, compilers for code parsing. Let's switch gears to graphs. I think a lot of engineers underestimate how often graphs pop up in real-world applications.
Oh, absolutely. Graphs are everywhere. Think about social networks like Meta. At its core, Meta is just a giant graph where users are nodes and friendships are edges.
And all those people you may know suggestions, that's graph traversal algorithms in action, finding paths between nodes to identify potential connections.
Exactly. They're using algorithms like breadth-first search or depth-first search to explore the graph and discover these connections. The challenge, of course, is that the graph is enormous. You can't just run a naive BFS on the entire meta-social graph.
So what do they do? How do they make it tractable?
They employ a whole host of techniques, including graph partitioning, distributed graph processing, and heuristics to guide the search. They might also use pre-computed data like common friends to speed up the process. The key is to break the problem down into smaller, more manageable chunks and to leverage domain-specific knowledge to prune the search space. This can also be seen when using Google Maps.
Okay, graph partitioning makes sense. Break the big problem into smaller problems. Any other surprising graph applications?
How about recommendation engines? Amazon, for example, uses graph databases to model customer behavior and product relationships. They can represent products as nodes and relationships like frequently bought together or customers who bought this also bought that as edges.
So, if you buy a book on data structures, Amazon might recommend a book on algorithms because those two nodes are highly connected in their product graph.
Precisely, and they can use graph algorithms to find similar products or to identify customers with similar tastes. It's a powerful way to personalize recommendations and increase sales. Again, the scale is mind-boggling. They're dealing with billions of products and hundreds of millions of customers.
Okay, so we've covered trees and graphs. What about heaps? I feel like heaps are often overlooked, but they're incredibly useful for priority queues.
Absolutely. Heaps are the unsung heroes of many systems. Think about task scheduling in an operating system. The OS needs to decide which process to run next, and it typically prioritizes processes based on factors like urgency and resource requirements.
And a heap is the perfect data structure for maintaining a priority queue, allowing the OS to quickly find the highest priority process.
Exactly. The OS can insert new processes into the heap as they become ready to run, and it can efficiently extract the highest priority process whenever the CPU becomes available. It's a classic application of heaps, and it's essential for ensuring that the system runs smoothly and efficiently.
So, OS task scheduling is a great example. Where else do heaps come in handy?
Think about Dijkstra's algorithm for finding the shortest path in a graph. Dijkstra's algorithm relies on a priority queue to keep track of the nodes that need to be visited. A heap is the perfect data structure for implementing this priority queue, allowing the algorithm to quickly find the node with the smallest distance from the source.
So, heaps are not just for scheduling tasks, they're also fundamental to many graph algorithms. Okay, Parth, this has been an incredibly insightful. Thanks for demystifying the world beyond arrays and hash maps.
My pleasure, Shreya. Remember, folks, data structures are the secret sauce of efficient software. Choose wisely, and your code will thank you.
And remember, folks, don't be afraid to get your hands dirty. Sometimes the best solution is the one you build yourself.